my website if you want to watch it. That link to the website is a course material. Syllabus and everything else is not everything because, for example, Siva's textbook is not there because I don't have copyright to do that. To do that. The rest it is there. You start already? Okay. We have about 2 minutes to wait for everyone else and we will start. Any question for me about the content of the class or anything? Homework? Did you do homework? Homework? Who finished the homework? Homework 2. Homework 2. You take a look at it? Yes, you plan to see TA, Arya on Friday, on last Friday. Did you meet him? This homework, do you have access to last year's homework? Yes and no?
Yeah.
Okay, the link is in the syllabus and you may go and take a look on last year's homework. How about last year's exam?
Yeah.
Did you try that? Okay, exam is not like quiz that when you do it wrong you get 9. It's not like that. When you do it wrong you get 0. Sometimes, especially true and false, true or false, you get -1. Okay. Practice that. Please bring your IDs. Okay, yes.
Is it like that for the first bronze as well? If you do all the work and you miss like one number, you still get a 0?
On the exam?
Yeah, it's like first one.
I don't know how to make the exam yet, but typically you get something. Okay. If it is true or false or multiple choice, there will be penalty for that. Okay, to prevent anyone from just random guess. Okay, last and second. Anything to say? We should start a little bit early. Not a little bit early. Okay, it's 11. It's my time. Any question on last lecture of the trip? No, right? Last time we talked about this. We talked about settling equation, terminal velocity equation in the SI unit and field unit. We talk about how to calculate drag coefficient. We talk about Reynolds number equation. Actually, we skipped this, but you should be able to do it. Okay, that number, you should be able to find it. We talk about retention time, equation for horizontal separator, equation for vertical separator. We talk about the shaft, seam to seam length, and the shaft. Okay, recommendation for the retention time and how we calculate retention time. Okay, by now you should be able to calculate retention time. Okay, and we already know that it depends on whether it's half full, 1/3 full, 1/4 full, or something. Okay, we have we talk about this using the chart. Okay, the way to read the chart is you need to read this first. That's it, very easy. And we have several charts. Gas capacity, liquid capacity, we have to check both. Okay, for vertical separator, we check both gas capacity and liquid capacity. It should handle both gas phase and liquid phase. Horizontal separator, we check both gas capacity, so this one is called gas capacity, and we check liquid capacity. So this one is liquid capacity. So we check both of them. Alright. This is a summary of the equation. Equation for vertical separator, there are two equations. Okay. For vertical separator, there is equation for gas capacity and liquid capacity. So both of these are what? Gas capacity or liquid capacity? Gas capacity. Okay. Let's go back a little bit. Seam length. Okay. Horizontal separator. This equation is gas capacity equation. Okay. And we have horizontal separator. This is half full. right? And we have liquid capacity equation, okay, for horizontal separator. Then we have okay, vertical separator, gas capacity equation, and also liquid capacity equation for vertical separator. When we look at the liquid capacity equation, that formula, is that going to be the same as the horizontal separator? Is it the same? No, it's not quite the same because horizontal separator is just half full. Okay? When it's half full in horizontal separator, we fill it this way, right? That is the volume. Vertical separator, this is a volume based on height. Okay? So for each type of separator, we have two kind of equation: gas equation, or gas capacity equation, liquid capacity equation. Today we're going to talk about how we use it. Okay? How exactly that we're going to use it. 90% of the time we use chart. Okay, that's 90% of the time. 10% of the time, Zoko. Okay. 10% of the time we have to use this equation. Why is that?
I guess we don't have the insert in the charts.
We don't
Have the inserts in the charts.
We don't have answer. Which case that we don't have answer from the chart? Next, okay, next you. What's your name, sir? Mil. What's that? Milik. What's your name, sir? Yeah. Lorivaldo. So, what is that 10% of the time that we don't use the chart? When do we not use the chart? When do we have to do this calculation? Okay, let me ask you this. Did I ever talk about that? Was it in the slides somewhere? Like in the very beginning? Oh, you did not read that? Is that what happened? Is that what happened? Is it? Really model? Oh, I'm sorry, you're signing that, right? You finished that signing? Okay, next, Alderson or something? What's your name? Allison. Last name? Okay, Mr. I'm sorry, but okay. When do we not use the chart?
Troubleshoot processing problem.
Okay, yeah. So you read it, you say, maybe just right now. Okay, you need to know that, okay, 90% of the time we use the chart, and when do we not use the chart? When do we require more calculation? And you need to know all this. Okay, this time, today we're going to show you how to do that calculation. From the theory, Christian with a K, not here. Vadeste, Kashamba, Vadeste. How do we derive the liquid capacity equation for vertical separator? How was the derivation done? Liquid capacity for vertical separator is this equation. Where does that come from? Okay, next you what's your name, sir? Richard, where does that equation come from? Okay, next to you, what's your name, sir? Pedro, where does that come from? I did not test you to derive that, okay? But at least you need to know where that comes from. Most of the time is just this. Retention time equal to volume divided by flow rate. Just that. This is where it comes from, for liquid capacity equation. Okay. That is also true for horizontal separator. Retention time equal to volume divided by flow rate. That's what it is. But for vertical separator, okay, next, what's the name? Leonardo? Is that your name? Okay, for gas capacity equation, how do they derive it? That's gas capacity equation. Oh, that's liquid. Gas capacity equation. That equation for vertical separator, where does that come from? Not the derivation part, but conceptually, how do they get that? Density. Do we use retention time concept over there? Sometimes we don't know about how they derive. It's maybe a little bit long, but you should be able to talk about it. Okay, so that they think that we know it. Okay, maybe the way that this comes from is based on terminal velocity. Okay, and actual velocity inside. You see this velocity, actual gas velocity is volumetric flow rate divided by cross-section area of the flow. That is actual velocity going up. Okay. Settling velocity is another equation that is terminal velocity equation. We compare those two, okay, we make them equal to each other, and that's where we say, okay, we use Vt equal to Vg, then do some rearrange, we get that, okay? So gas capacity equation is based on settling velocity and the velocity of gas inside. If settling velocity is more, it's good. If gas velocity that going up is more than the settling velocity, it's not good. We're gonna plug or saturate the mist extractor. Make sense to you? So we compare those two. Yeah, 55. Christian Barajas? No. Joseph J. Black? Not here. Oh. Okay, you signed it too. Okay, I'm sorry. Feng De Bui? Not here. Christian with K. Dominguez? Not here. Gatimbrerizo Mukio? Not here. Angel Evan Munoz? Not here. Katie S. Ramirez? Not here. Luis F. Rodriguez? Not here, okay. Omar? Not here, okay. So everyone else is here, is it? Alright. Let's see how we use it. Okay. At the end of last class, I showed you the chart and this kind of table, but haven't gone through it. Let's take a look a little bit. Okay, this one is for vertical low pressure separator. Look at the working pressure. When you say 125, they consider it as low pressure. Okay. There's a model number, diameter in inch, height in feet. Okay. Standard valve, the valve that they use, chipping weight. Most of the time we concerned with this working pressure and that size. Alright? And okay. The next one, this one is more detailed. It says, okay, if you use 24 by 5, how much is going to be settling volume, right, for this separator? They say, okay, oil and gas separator, we have settling volume of 0.65. How do we use that number? Yes?
0.65 what?
Barrel. Settling volume in the unit of barrel. How do we use this number? You have to use it somehow, okay? Oil, gas, water separator has settling volume of 1.10. Okay. How do we use that? How do we use 0.65? Based on what I taught you. We cannot use it. Can we convert that to retention time? Maybe. Mr. Lee?
Yes.
Yes, okay, very good. And how do we know retention time that we need? How much is retention time do we need? Is that, do you need to write that number in? Not really. There's a table, right? There's a table talking about retention time. For example, this table. Based on the API gravity, there's a retention time. How many minutes? This at least. Okay? Good? So this is the retention time. Let's say my oil is 30 degree API gravity. We need about 2 minutes. Okay? Maybe I have foam. Okay, let's multiply by 4. 8 minutes. 8 minute retention time. And of course, I have this equation. Time in minute equal to 1440 V barrel divided by W barrel per day. Okay? And I have settling volume 0.65. How do we use it instantly? Please,
Plug the 0.65 into the
0.65. That is volume
yeah.
divided by maybe flow rate. Barrel per day. That will give us time. Okay? Of course, we do unit conversion and it happened to be 1,440. Okay? So based on this retention time in volume, we can calculate, and if we know the flow rate of liquid, we can calculate retention time. Then we can check if that retention time is less than what required or more than what required. Make sense? Yes? Okay. Any question on how to use this retention time? If you can use 0.65, you can use 1.612, right? So let's go back to my equation again. Retention time in minute equal to volume, that will be settling volume, okay, divided by flow rate, and multiply by 1,440 to the unit conversion to make time. So what I do is going to be, if I have liquid flow rate or oil flow rate, 50 barrel per day, I do 1440 multiplied by settling volume, which is from that divided by 50 barrel per day. And this gives me retention time that I have. Okay. This is going to be available retention time. So this means this separator gives me that much retention time. Good? Let's say we use second separator. We use this one, 1.01. I have 1440 multiplied by 1.01 divided by 50 barrel per day. So I have 1440 divided by 50 multiplied by 1.01. I get 29 minutes. So this separator gives me 29 minutes of retention time, for example. You got it? Alright, this is so this means we can do faster than, if we end up use this separator, we can do faster. If I use 50 barrel per day, it gives me 29, that's too much. Okay, we may just need 8. If I do 3 times faster, like 150 barrel per day, it will give me retention time of 10 minutes. You see what I'm saying? That's still, we still have available retention time more than the required retention time. Required retention time come from that table. This one. Good? No question for me? Alright. So this chart gives me settling volume for the vertical separator. Alright. Now there's a problem with this. Okay. This is if we operate it at the way that they recommend to operate. They recommend half full, we operate half full. If we decide to operate less than half full, maybe we have less settling volume. You see what I'm saying? So the amount, the liquid height in the separator is actually matter. So if we don't do something that the manufacturer recommends, we use a full calculation. Okay, the full calculation. Alright, here's another chart for vertical high pressure. So this one is high pressure, it has several sides, shipping weight. Okay, and it has the note for other pressure. We still have up to 2000 psig. They save it. Alright, retention time, settling volume, gas, oil, water. If we want to do three-phase separation, that is settling volume and calculate with that. Settling volume we typically use for liquid phase. Okay. If we use for gas phase, we need the retention time for gas phase. Okay. This is for liquid capacity. Okay. For gas phase, we mainly use a settling equation or use a chart. Okay. Let's see the full form. This is for gas. Equation for gas for vertical and horizontal. We talk about this chart and we know how to calculate the retention time in liquid phase, also in gas phase, if we have the table for gas phase. Okay. Look at this one. Settling volume of standard horizontal low pressure. If you operate half full, I have settling volume of 1.55. 1/3 full, 0.89. Quarter full, 0.59. Okay, next behind Leonardo, what's your name, sir? Yes.
Scott.
Scott. Why those numbers keep going down?
Because it's horizontal, so you've got less areas.
Why do we have less settling volume?
Because the area in the
Is it about the area or volume? So this means this chart is about settling volume of liquid phase. See what I'm saying? If we operate half full, we get that much for settling to happen to calculate retention time. That's about 1.55 barrel. Okay. If I operate just quarter full, maybe just this much. So I even have less, it can handle less amount of liquid. So this chart is correspond to the liquid volume in the separator. Make sense to you, Scott? Yeah, alright. So this is to do with liquid phase retention time. Do not use this for gas phase, okay? If you use it for gas phase, that's wrong. Gas phase, use a chart. Okay. Another one is different size. Okay. Different size. And it tells, okay, different settling volume. So half full has more volume than quarter full. More volume of liquid phase, not gas phase. What do I do with full calculation? Okay, let's say in the exam, I know that you can use a chart and we use a chart. Chart is 5 point and okay. Another 40 point come from this calculation. Let's take a look how we do it. In this situation, we have 10 million standard cubic foot per day at specific gravity of 0.6. Okay. We have liquid at 2000 barrels per day at 40 degree API. We operate it at 1000 psia. Okay. Operating temperature 60 F. Diameter of the droplet. Okay. 140 micron. So this is for gas liquid separation. Okay. Gas liquid separation. We have mu G viscosity of gas phase is 0.013 centipoint at that pressure and that temperature. Right? We need retention time about 3 minutes. Size a vertical separator. So we want to separate gas and liquid phase. Okay. Alright, when we separate gas and liquid phase, okay, what we do now is step number 1, calculate C sub D, drag coefficient. So for vertical separator and gas capacity, Arnold-Stewart compare settling velocity with gas velocity inside, and they come up with the gas equation, right? So at the end we get settling velocity. Okay, this settling velocity we use okay, settling velocity. After we get settling velocity, step 1, we will go back to this. We get settling velocity. You see that 0.866? That is settling velocity. After we get settling velocity, we can recalculate Reynolds number. Okay. When we look at this Reynolds number, viscosity is viscosity of gas phase. Okay, that is viscosity of gas phase. So we are asking ourselves the question that if we have small water droplet in the gas phase, will it go down or it go up? Okay, that's the question that we are asking. Okay, that's why we try to calculate drag coefficient. That drag coefficient is the drag coefficient of liquid droplet falling down and have gas flow around it. Okay. So if we know friction around that, we know Reynolds number, we can calculate terminal velocity. So to do all that, step 1, we calculate drag coefficient. To do drag coefficient, we calculate number 1, rho L, okay, density of liquid phase. Density of gas phase. Density of gas phase, we have formula 2.7 gamma P over Tz. Where does that equation come from? Next is Scott, what's your name?
Ricky.
Ricky. Okay. Where does that equation come from, sir? Correct. With some math, we get that. Okay. Reading the chart, we get the factor. Density of the gas, substitute the number in, we get that much. Okay. Okay, look, we try to calculate drag coefficient. But the recommendation from Arnold-Stewart says, let's assume the initial value of drag coefficient to be 0.34. Okay. You may remember that if we have laminar flow or Reynolds number less than 1, we don't need the iterative method. But this is a case where we need iterative method. Okay. So we assume drag coefficient equal to 0.34. Substituting this equation. Where does that equation come from? Next to Scott, what's your name, sir? No. What's your name? Ricky, next to Ricky. Hunter, where does that come from? Previous slide, of course. Previous slide. It's somewhere from the previous slide. Is it this one? Okay, this one is SI. Is it this one? Or maybe that one? One of that, okay. Vt equal to some coefficient multiplied by delta St d sub m squared over mu. Mu is viscosity of the continuous phase, which is gas. Okay. Delta St different in the specific gravity. Okay, when we go back there, we see, okay, put the number in, I get that. Delta St, that can be used instead of delta St. Okay. And put maybe this is another equation. Okay, this equation is the form before do the substitution. Okay, notice that we still have C sub D. But the terminal velocity equation that I show you in the yellow box, it doesn't have C sub D. You see that? This one doesn't have C sub D, but that one has C sub D. So that one is even before we do anything. So it do drag force equal to buoyancy force, do some math, and they get that equation. Okay? Before substitution of C sub D. So that equation probably come from this slide. Got it? So write that too and that too. The bottom one is SI unit, the top one is field unit. Alright, we substitute the value of C sub D, dm, everything else, we get terminal velocity. Then what's next? Terminal velocity. I substitute everything and get terminal velocity of 0.866. Okay? That 0.866 is a terminal velocity by assuming that C sub D equal to 0.34. Okay? We always assume that as the starting point. If we assume something else, it may not converge. Okay? Yes, we start with that.
0.866 feet per second, meters per second.
Feet per second in field unit. This is feet per second in field unit. So that corresponds to the equation in the field unit. Then, okay, this is a derivation on how we get 2.7. Okay, it is from PV equal to Z nRT like Ricky told me. Okay, put everything in to Reynolds number equation. So I have 0.866 for that velocity, right? Calculate it again, I get Reynolds number of 100 and something. That's a lot. Is that a lot? Okay, next to Hunter. What's your name, sir? Grant. Is that turbulent flow or laminar flow? Grant. How do you know that? What is critical Reynolds number for this case? Critical Reynolds number for this case equal to 1. And that number is more than 1. Okay? So this is turbulent flow. For turbulent flow, drag coefficient is that formula. So once we know Reynolds number, okay, if you use understood formula, that is a formula, it gets similar answer. Once we know Reynolds number, we can substitute the Reynolds number into drag coefficient formula. We get the new one for the drag coefficient, 0.711. Okay. Once we know that drag coefficient 0.711, we go back to this slide. Substitute that 0.711 over there. Calculate terminal velocity again. We will get something else. Okay. We will get the new terminal velocity. And that new terminal velocity I got 0.579. After I get that 0.579, substitute that in there, I get new drag coefficient of 0.82.
How do you need a new Reynolds number?
Reynolds number of the second iteration, 118.
Yeah.
So first iteration I get that. What's your question?
Well, you said when you plug 0.579 in, you circle the Reynolds number equation, but said you get a
0.579, replace that number. This will make that number change to that.
Yep.
Good?
Yep.
Alright. Repeat the process. Get CD, put CD back into Reynolds number. Once get Reynolds number, plug it back to the drag coefficient equation. We do that several times. Eventually, it will stop fluctuating which should end up to be 0.851. Good?
Where'd you get the critical Reynolds number of 1?
Critical Reynolds number equal to 1 come from experiment.
Holy crap.
For flow in the pipe is 2100, right? For this case, is flow around a spherical shape. For flow around a spherical shape, they found that critical Reynolds number about 1 made the transition from laminar to transient flow and eventually turbulent. Good? Alright. So for turbulent flow, inside the separator, we successfully get the right drag coefficient and of course the right terminal velocity. Okay, now the question is that terminal velocity higher or lower than the actual velocity in the pipe? Okay, we should account for everything for the terminal velocity in the pipe. You see this 0.85. Okay, we can calculate the gas capacity. Once we know the drag coefficient, put drag coefficient over that. Alright? And this equation already take care of those comparisons. This equation is derived based on the comparison between upward actual velocity and the terminal velocity in the separator. So this equation take care of the calculation comparison already. Once I plug that in, so this is the gas capacity equation for the vertical separator, I get that number. Good? Alright, step 1 is done. So let's say I want to do the test on this, and I know that during the test you cannot do this iteration thing. You can, it's too much. I can just tell you the drag coefficient, just that, right? Alright, that is small d in each unit. Now we take out kind of gas. At least the diameter of the separator has to be that big. If you ever, I ask you, okay, we have maybe 20 inch diameter and 24 inch, which one do you want? If you do 20, that's wrong. We should do at least 21.9 or more than that. Good? What about liquid phase? Okay, liquid phase is d squared h TR/QL over 0.12. So this is a liquid phase calculation based on the retention time. Oh, we have 40 degree API. Okay, 40 degree API, how much retention time do I need for liquid phase? I go back to that. Okay, maybe 1 minute, 2 minutes may be fine, 3 minutes will be like, even if we have foam, if we have like 0.5 multiplied by 4, 3 minutes will take care of it for sure, right? At least 30 seconds, okay? If we have CO2, we do minimum of 5 minutes. So this is how we know the retention time. In this case, Arnold Stroh suggests retention time of 3 minutes. Let's use retention time of 3 minutes for this design. Okay. This is retention time of, is that gas phase or liquid phase? Grant? Gas phase or liquid phase? Oh, very good. That's correct. It's for liquid phase. So that's retention for liquid phase. We already know the diameter based on the gas phase calculation that you go through the pain for C sub T, right? Okay, for liquid capacity, it depends on how much is the volume in the tank. Okay, so that number obviously TR will be 3, right? We want to do 3 minutes. What about QL? What do I put there? QL will be 2000 because this time we have 2000 barrels. So that number will be 2000 2000. That number will be 3. Diameter will be at least that. And we have height. Okay. Height of liquid phase. Good. Alright. After we calculate liquid capacity, then we calculate seam to seam length. Then slenderness ratio should be between 3 and 4. So now let's take a look at this table. The way that this table was generated is based on retention time of 3 minutes. Available diameter that is more than 21 point something that we have, more than 21.9, more than 22 is that. Okay? Alright. We need to know the height. Okay? This height is just the height in separator, liquid height that we try to operate. Okay? So let's say I try to use 24 inch and I come up with that height. How do I come up with that height? Grant? How do I come up with that height? Where does that height come from? Assuming or what? No, I don't think it's in. Is it in the previous equation? Okay, I have diameter. Oh yeah, it's in previous equation. I have height. So that the instead of 21.9, I substitute it with 24. I put 24 over there. I have the rest, then I can calculate height, right? So this tells me if my diameter is that much, my height will be that much. If my diameter is that much, my height will be that much. Good? Then I can calculate seam to seam length. Seam to seam length comes from the equation that you have to write down when you go to take the test. For vertical separator, seam to seam length comes from those two equations. Slide 76. Slide 76 have seam to seam length equation. Once we know seam to seam length, we can calculate the slenderness ratio. What is the equation for slenderness ratio? LSS over diameter in feet. So what I do is I use liquid capacity equation based on that and that 3 minutes. I get the height. From the height, I can calculate seam to seam length, right? L plus 40 plus D divided everything divided by 40. And at the end, I can calculate slenderness ratio. And okay, let's disregard those 1 minute and 2 minutes because in this question we forced to use 3 minute retention time. Look at the slenderness ratio. 6.8 is not good. The recommendation is between 3 to 4. So 6.8 is not between 3 to 4. 4.4 is not in between 3 to 4. But that one is between 3 to 4. So we use it. Okay. We select this one. Okay. When we select this one, I go back here, I select 36 inch by 10 feet. But when you look at this height, 10 feet, how much is 10 feet? How many inch? Next to Grant, what's your name, sir? Jose. For 10 feet, we have how many inch? 120. But that is not 120. Is that okay? What is that height, by the way? What is that height? Height of the liquid phase. So this means obviously that seam to seam length doesn't use that height in calculation. You know, it uses what height? Height from this kind of table. You see, for the size of 36, we have two options. Option 1, 36 by 10 feet, 36 by 15 feet. We have those options. So I use 10 feet to calculate simplicity length. Okay. I tried this morning, I don't get 9.6, I get 9.2. I go back and I use another equation